All right, welcome everybody to Climate and Weather. How do they connect? My name is Rick Knight. I'm the moderator. And scientists are sometimes asked if a weather catastrophe was caused by climate change. Their answer can sometimes cause more confusion than clarification because there is no single cause for any weather event. Every such event arises from the interplay of many factors, one of which is the excess global heat buildup that we call climate change. But what role does it play in specific events? I'm really honored to introduce two of the nation's top scientists to unravel the mysteries behind this vital question. Dr. Anthony Broccoli, to my left, is Professor of Atmospheric Science and Chair of the Department of Environmental Sciences at Rutgers University, where he also serves as co-director of the Rutgers Climate Institute. His primary research interest is climate dynamics, especially the simulation of past climates and climate change. He currently serves as co-chief editor of the Journal of Climate, and he has been a contributor and reviewer for the IPCC. Prior to coming to Rutgers, Dr. Broccoli spent 21 years at NOAA's Geophysical Fluid Dynamics Laboratory in Princeton, one of the premier climate modeling centers of the world. He is a fellow of the American Meteorological Society and the American Association for the Advancement of Science. And Dr. Kirk Davidoff is an adjunct associate professor in the Department of Atmospheric and Oceanic Science at the University of Maryland. He received his PhD in meteorology from MIT in 1997. He's a climate dynamicist with interest in wind power forecasting and wind power climate interactions, the stratospheric water vapor budget, paleoclimate modeling, satellite climate monitoring, and the use of satellite data to improve climate models. Those are our panelists. We'll have two presentations from the two panelists, and then we'll have plenty of time to open up the floor for questions, because I'm sure you all have a lot of questions about how these things work and what's the effect of El Nino, what can you say about extreme weather events, and we need to have the testimony of these experts at our disposal. So we're going to start with Dr. Tony Broccoli. Let's see, which one is that?
Thank you very much. It's a pleasure to be here this afternoon and try to set the stage a little bit on the question of climate change and extreme weather. And notice my subtitle about asking the right question, because I think that's really very important here. So we know the world is warming. You've seen graphs like this many times before, and I'm not going to spend very much time on this at all. Increase in global temperature is one of the fundamental characteristics of climate change, and it's understandable that that would be the case because what carbon dioxide is doing is adding to the heating of Earth's surface. But the question is, how does this globally averaged warming relate to some of the things we see in terms of extreme weather and climate? And as I prefaced with my subtitle, asking the right question is really important here because we sometimes hear people talk about whether extreme weather events have been caused by climate change. And it's not always clear what that means, but one reasonable definition would be an event that would not have taken place if the climate was the same as it was during pre-industrial times. And as a practical matter, this is a difficult criterion to meet because we know that even if the climate wasn't changing, having a longer period of time to observe something means it's much more likely that something extreme would occur. So when something more extreme than what we've seen in the past happens, Is that because of climate change, or is that just because we finally saw something that nature would have provided in the first place? So it's summer now, and NBA season ended last night. They've awarded the Stanley Cup already, so it's definitely baseball season. And the Nationals are doing very well, which I'm sure makes the locals here quite happy. I want to offer a baseball analogy. Let's say there's an outfielder who's been around for a while, and he's got a pretty good batting average, but doesn't have a lot of home run power. And during the off season, he starts some weight training because he knows the way to big money is to hit home runs. And in his first at bat of the new season, he hits a majestic 470-foot home run. So was that home run caused by his off-season weight training? Well, you know, there are a number of possible answers. If you're his sports writer skeptic, you might say, of course not, one home run doesn't prove anything. It might have just been a fat pitch. Anybody could have crushed it. If you're his agent, then you might say, well, I knew all that off-season work would pay off. I bet he's going to win the home run title now that he has more strength. And then, of course, there's also that third possibility that we don't like to talk about too much. But the real issue here is that it's the wrong question. And you can probably see the flaws associated with trying to answer this question definitively, regardless of whether the answer is yes or no. And that's the problem here. The difference of opinion really arises as a consequence of asking a question that requires a yes or no answer. So what is a better question? Well, in this baseball analogy, a better question would be whether or not his off-season weight training has increased his probability of hitting a home run. And obviously, that's a question that requires a lot more evidence before you can answer that question. In the case of climate change, an analogous question is the right question. Has climate change altered the probabilities of experiencing certain kinds of weather or climate events? Yes, it's possible that climate change could cause an event to occur that would not have happened without climate change. But a better way to ask the question, because we only have limited evidence of what Mother Nature could produce without the effects of climate change, is has it altered the probabilities of these events? And Dr. Jim Hanson, who most of you probably know, has developed an excellent analogy that involves dice. And not the kind of fuzzy dice that you may have hanging from your, well, I hope you don't have hanging from your rearview mirrors. But in Jim Hanson's climate dice, before climate change, they're colored with 2 blue faces, 2 white faces, and 2 red faces, indicating colder than average, about average, and warmer than average temperatures. And in his analogy, what climate change does is cause one of those faces to go from blue to red. So now there's 3 red ones, 2 white ones, and only 1 blue one. The important thing there is that it's still possible to get unusually cold weather, but the chances of getting unusually warm weather have increased. And when we look at summer heat, and this is a paper by Jim Hanson and colleagues, we see that the probability of getting weather that could be defined as hot, very hot, or extremely hot, based on a 1951 through 1980 baseline, has increased. So those hot days that Jim and his colleagues defined as being the warmest third of the time during that 51 through 80 period is now occurring anywhere from 70 to 80% of the time. A very hot, which only had a few percent chance of occurring back in the baseline period, may now happen 20 or 30% of the time. And those rarest of hot periods, those extremely hot periods that used to happen just a fraction of a percent, may now happen as much as 10% of the time. So what we're seeing are changes in probabilities. And the observations show that daily temperature extremes and heat waves have become more common. And the IPCC reckoned that it is virtually certain that we would see the frequency of warm daily extremes increase and cold extremes decrease throughout the 21st century on a global scale. And they regarded it as very likely that heat waves would increase in length, frequency, and/or intensity over most land areas. What about heavy rain events? Over the United States, in the last 5 or 6 decades, we have seen in almost all areas a change in the amount of precipitation that comes from very heavy rain events. This doesn't necessarily require the total amount of precipitation to go up. It just means that more of that precipitation is coming from very heavy events. And projecting forward in time, the IPCC believes it's likely that the frequency of heavy precipitation will increase in the 21st century over many regions. That can imply changes in floods, but the causes of floods on a large scale are complex, and there's limited evidence to know whether or not this is happening. However, when we think about the smaller drainage basins and flash flooding events, increased heavy precipitation events would be expected to cause more flash flood events, although again, there are other factors in play there, like the increase in the amount of impervious surface in many drainage basins. There's also evidence that the IPCC gauged as median confidence that droughts will intensify in a number of places around the world. You see them listed there. And even in other places that short-term droughts, short-term dry spells might increase in frequency or length. So the picture is of a more extreme hydrologic cycle, both on the wet side and also on the dry side. Now, tropical cyclones are an area of focus going back to work that Kerry Emanuel of MIT did in the late 1980s. And there's a logical reason to think that tropical cyclones would be sensitive to climate change because they derive their energy from the warmth of the underlying ocean. It is likely that the average maximum wind speed of tropical cyclones, whether we call them typhoons, hurricanes, or cyclones, depends on the drainage basin. But globally, it's likely that the average maximum wind speed will increase during the coming century, although we don't know enough yet to say whether that will happen in every ocean basin. However, it's also likely, meaning a greater than 2/3 chance, that the overall number of tropical cyclones will either decrease or not change very much. So the future world in terms of hurricanes may be one in which they become more intense, but not necessarily increase in number. And this graphic just shows some results from a paper that was done at the NOAA Geophysical Fluid Dynamics Laboratory. The upper left showing storms from their hurricane model for the late 20th and early 21st century, the colors indicating the intensity of the storms, and then simulations from several different modeling frameworks of early and late 21st century conditions with more of these intense Category 4 and Category 5 storms, even though the overall number of storms may not increase at all. Now, being from New Jersey, I feel as if I have to say something about Hurricane Sandy, which almost 4 years ago now did this unusual left turn and made direct landfall on the New Jersey coast with a lot of damage ensuing in the New York, New Jersey metropolitan area. And there's been a lot of talk about the unusual weather pattern that was associated with Sandy and whether or not these unusual weather patterns are becoming more common. And indeed, if you compare the track of Sandy that you see on the left side of this panel with the tracks of all of the other previous tropical cyclones that passed within 50 miles of Atlantic City, Sandy is definitely on an unusual path. And there's been some work suggesting that maybe these unusual weather patterns where systems stall or take unusual turns are becoming more common. And in fact, one person associated with that work is my Rutgers colleague, Professor Jennifer Francis. But at this point, we just don't know if this is the case. This is still an area of active research. But what we do know is that the damage that Sandy caused, which was largely the result of storm surge flooding, is poised to increase dramatically as sea level rises. Sea level globally is now rising at a rate of about 3.5 millimeters per year, and there's evidence that this rate of sea level rise is accelerating. And taking this into account, while under today's conditions, some statistical estimates of the return period for an event like Sandy are in the range of hundreds to even maybe over 1,000 years, the flooding associated with Sandy by mid-century would have much shorter return periods. And by the end of the century, due to the increase in sea level, storms with the damage potential of Sandy might happen as frequently as every 3 to 5 years. And that's because the ongoing rise in sea level is raising the baseline for coastal flooding. So it won't take a storm as strong as Sandy to produce the same conditions. So I'll wrap it up here. My take-home message is climate change can alter the probability of occurrence of certain extreme weather events. Changes in the frequency of warm extremes, they're going up, and cold extremes, they're going down, have already been detected, as have changes in the frequency of heavy precipitation events. There are other types of extreme events that may also change in response to a changing climate, but such changes have not yet been unambiguously detected, and more research will be required to better evaluate their future likelihood. Part of the reason for that is the more extreme an event is, the more difficult it is to statistically know whether it's happening more frequently, whether the probability of that event has gone up. And there are risks in over-attributing extreme events to climate change. Very often, when I speak to people who are very concerned about climate change, they find that talking about extreme weather events is a way to motivate people who might otherwise be interested. But it's important to be careful there, because if we attribute events to climate change that aren't really associated with climate change, that then there's a risk that when those events don't happen more frequently in the future, that will be used as evidence that climate change isn't occurring. So with that, I'll end and look forward to some discussion later.
Let me test this one. Okay. Thank you very much. Our next speaker, and I'm sorry we don't have name tags here, but in case you did come in a little bit late, to my left is Dr. Tony Broccoli of Rutgers, and now coming up to the podium is Dr. Kirk Davidoff of the University of Maryland. Dan?
Yeah, thanks so much. It's great to have an opportunity to talk to you all. I'm really impressed with Citizens Climate Lobby. I hadn't really delved into the organization until coming here this morning, but you guys are doing great work, and it's an honor to be here. So I'm an adjunct at University of Maryland, and I used to teach there full-time for a bunch of years, but about 6 years ago, I took a job as chief scientist at a company called NDA Information Systems, where we provide weather forecasts to the energy and ag industries. So they hired me because they understood I'd done some work on interactions of wind power and climate, and they were hearing from their energy trading clients that it wasn't enough anymore to have just a prediction of temperature from which they could calculate how much electrical demand there might be tomorrow at a certain time of day when they wanted to buy or sell electrical power, but that they also needed to know how much wind generation there was going to be in the Texas grid, which is called ERCOT, and the Midwest electrical grid. And so, I set that up for them, and in the course I've, learned a little bit about how weather forecasting is used in the real world, which I had never really thought about too much before. In fact, when I first arrived there, I thought, that's funny, why would anyone pay you for a weather forecast when we can go to weather.gov and get the weather forecast? And on bad days, I still wonder that, but but the short answer is that the people we're dealing with aren't really interested in the weather for its own sake. They're interested in the weather for some particular purpose. They want to know about electrical demand or natural gas demand, whatever. And they want things to be translated into terms that are particularly relevant to their particular concerns. So, it's some of this is hand-holding, and some of it is just very clear communication, and some of it is just providing large amounts of data in forms that are simple and easy to digest for the kinds of models that they use. So with that, Tony laid out the basics, the gist of this problem really clearly, and I don't disagree with anything he said. So I'm really just going to talk a little bit about how we encounter climate change as a problem in the commercial weather forecasting business. And I hope that will be of some interest and maybe provoke some interesting conversation or questions. So as I think about it, there are about 3 ways we can think about climate change and weather. One, and weather forecasting enterprise, right? So one would be the short-range weather forecast, so out the next hour to the next 5 days or so. And that's the realm where numerical weather prediction models are dominant, where modern science has enabled us to do a very good job forecasting the weather. Beyond that is the long-range weather forecast, which you might also call a short-range climate forecast, because that's really what it is. And that's taking what's observed at the current state of the atmosphere and, importantly, the oceans, and asking, what does that imply for, say, the climate of next month relative to the usual climate of next month? And those things might be different, say, because the Western Tropical Pacific is a lot warmer this month than it normally would be. And then the last thing that I'll talk about, and really I think it's the most important aspect of all this for our business, is what's the impact of things that we are doing about climate change for the interest in weather forecasts. Okay, so short-term weather prediction. So as I said, most of the way we do weather forecasting now is we run these models that embody our understanding of the physics and chemistry of the atmosphere. So they're called numerical weather prediction models, right? And they just integrate the equations of motion, Newton's equations, F equals ma, and some equations about how radiation moves around in the atmosphere to say what's going to happen based on what the state of the atmosphere is right now. What is the state of the atmosphere going to be in 10 seconds, and then in another 10 seconds, and another 10 seconds, and so on and they usually run them anywhere from 3 days to, well, from 19 hours to 3 days to 2 weeks or so. And those models are great out for the next couple of days, and then they trail off and still beyond that, not because they're bad models, but because it's probably an inherently impossible problem to predict the detailed weather beyond that period. So probably the universe does not know yet what the weather is going to be in detail, say on July 15th. So the impact of climate change on that problem is that you have to make sure when you run those models that you include up-to-date conditions of the atmosphere. So you might get the wrong answer about what the weather will be tomorrow, the next day, or the next day, if, say, you didn't have enough carbon dioxide in the atmosphere. It would be a small effect on today and tomorrow and so on's weather. But more importantly, you need to know what today's weather is at the moment so that you can integrate from there. What's the difference going to be? Because that's what those models are really doing. You have to figure out what the difference is going to be from today's weather, so you have to know the present conditions very precisely. And then the other thing that's probably more on the minds of our clients is context setting. So when we provide clients, very often those are in the form of an anomaly. So we'll provide a forecast, like someone who's interested in trading energy or someone who's interested in knowing what the soybean crop is going to be in Iowa this year. What they care about is how this week, tomorrow's weather or this week's weather or next month's weather compares to what it's been like recently. Because they're using their experience of what it's been like recently to drive their models of how much electricity we're going to need tomorrow, right? Because the electrical system changes pretty rapidly. It's not very useful to say that the temperature is like 5 degrees warmer tomorrow than it was averaged over the whole century, because their electrical model only corresponds to the electrical demand that's existed on the grid for, say, the last 5 or 10 years, right? So we need to be providing forecasts in the context of what's happened in the recent period. And that means that in our operations, we have to have up-to-date statistics because the climate has changed, say, from 20 years ago or 30 years ago to the last decade. And as I'll say before, that's a fairly subtle, in a moment, that's a fairly subtle effect. So here's the forecast for today's high temperature, right? And again, this is in anomaly form. So this is the deviation in degrees Fahrenheit. You can see a scale at the bottom of there of today's weather from the normal for this day. Right? And look at the magnitude of those deviations. Now, I'm cheating a little bit because there's a fairly extreme event happening right now in the Southwest. It's going to be, the high in Phoenix today, I think, is going to be up around 115 or something, which really is quite unusual. They'll probably set a record, and at least in some of those cities down there. And you can see that in that little bright red corner down in the Southwest there, where the anomaly looks like it's about 20 degrees Fahrenheit. Right? So think about that in the context of what Tony talked about. So how much has climate change affected the likelihood of that? Let's compare these things a little bit. So here's another example. This is the temperature at a little bit higher in the atmosphere taken by a radiosonde in the context of the whole climatology of temperature observations for the last 30, 40 years. And you can see that the little red circle at the top there, that was this morning's observation in Tucson. And you can see that it's just about a little bit above the record. It's the warmest it's ever been at that location, right? But by how much? Right? By quite a lot. It looks like that's about, what are we at? Like about 7 degrees Celsius, so 13 or so degrees Fahrenheit warmer than the usual for that location and that time. So, how does that compare to the climate trends of the last 30 years, right? So here's the US average temperature over the last century, and you can see that right now, this is going to be a very warm June in particular, but if you average over the last couple of years, then it's fair to say we're about a degree warmer now, a degree Celsius, so warmer than we have been averaged over the century, right? So presumably, the answer is that a 1 degree warming of the whole US has had a fairly small influence on the likelihood of having a 12 degree, or whatever that was, like a 7 degree record in degrees Celsius at, on one particular day. And I have a map up there that shows that 1 degree it's a little unfair to just take wide averages. You maybe want to set the context a little more regionally. So the figure on the right shows the anomaly of the last 5 years relative to the century. And that's showing that over the western part of the US, it's been larger than a degree warmer than average, and in the eastern part, less than a degree average. So the impact on the weather of climate change over that location is larger in the west than in the east, and you'd want to say, okay, well, so of the 7 degrees by which this event was warmer than average, maybe about 1.5 degrees of that was caused by climate change. Okay, and in fact, that would have, if we look back at that at that red dot up there, if you reduce that by about 1.5 degrees, it would be below that skinny red line, and so it wouldn't have been a record. So that's just a worked example, as it were, of Tony's point about, likelihoods and the shift of means resulting in a change in probability. So with precipitation, I just wanted to throw this up as well. Again, that changes, we can see appreciable changes. There's more precipitation per year, typically over the world as a result of a warmer atmosphere, over land areas, as a result of a warmer atmosphere that can carry a little more water. Some places are wetter, some places are drier. Averaged over the whole planet, it's hard to have any big change in precipitation for more complicated reasons, but you can certainly change the distribution. But if you look at the magnitude of these changes, these are on the order of a centimeter per year trend per decade. So so over 30 years, you'd get like an inch more precipitation over a year in the bluest areas of this map, right? So that's a lot as you add up and increase and go on over time. But in the context of tomorrow's weather, where we might get an inch of rain from a big rainstorm in a day, and that wouldn't be anything spectacular, it's going to be very, very hard to attribute particular rain events to a long-term trend. So that's the short-term prediction. With long-term prediction, this gets to be a little more directly related to what we do. So with short-term prediction, the main issue is just to make sure that our context is right, that we're giving people information about a period that's comparable to the period that they think about when they're thinking about the things that they care about, energy demand or agricultural production or something like that. With long-term predictions, the models don't work as well. So we need to think more about statistical methods, and we might use a method like what I've shown down there below. So I'll break that out into separate chunks there. So we're saying that the temperature, say next month, is going to be a function of a bunch of things that we know about, and then I didn't include a big error term at the end, which would be all the stuff that we don't know about or that is undetermined in the universe, but it just has to do with the chaotic workings of the weather system. But the first one might be a trend. We know the world is getting warmer. So if we're asking how different will next month be than the same period average over the last 10 years, then we have to think, well, how much warmer is the world getting over that time? And add in the trend over that period. Now, typically that's going to be on the order of a couple of tenths degrees Celsius, depending on how far back we're taking our average period. Then we might ask, well, how are some of the large global oscillations that might impact local weather going to work themselves out in this context? So because this summer we're in this transition period from an El Nino to maybe to a La Nina, although we'll see. We might look at last summer's situation where we had a strong El Nino developing in place and say, well, how much of an impact does that have over the United States? And those impacts are on the order of like ½ degree Celsius. Okay? And then we might think about, well, how warm has it been this month? And understand that anomalies tend to persist a little while. If it's been about ½ degree warmer than normal this month, then you want to make a guess that probably we're about ¼ degree warmer next month. So in discussing all this, my point is to say that climate change on the issue, in the context of making a forecast for next month, what are average conditions going to be like in July or August in DC or some other location, is going to be a factor we shouldn't ignore, but it's going to be fairly small compared to the other things that are likely driving weather. Right? It's going to be at about a third or a quarter of the magnitude of something like a strong El Nino acting next month. And here are just a couple of maps that kind of bear that out. So here's a 30-year normal temperature for July. Right? Here's the last year's departure from normal. These are in Fahrenheit. These are designed for our clients and grab them off our own website. And you can see that we had about a 4-degree negative anomaly over western Colorado last summer, right? So that's 2 degrees Celsius or so. So that's quite large, right? So in western Colorado last July, it was the particularities of weather wiped out a century's worth or a half century's worth of global warming, right? It was as the temperature in western Colorado last summer was about the same as you would have expected on average in 1950 or something. Whereas up in Washington, where it was like 3 degrees Celsius warmer than average, you had extra warming. It was very warm over there relative to what you would have expected in the 1950s. let's see. Oh yeah, here we go. So this is kind of interesting. If you look at, we go back and forth between these two things, this is showing the difference in last year's July temperature anomaly relative to a 10-year normal. So this is what it looks like compared to just the last 10 years. And this is what it looks like compared to the 30 years from 1970 to 2000. And what you can see is that compared to the last 10 years, the anomaly in western Colorado and eastern Utah looked really extreme. It was really cold. But compared to the period 1970 to 2000, because we've warmed up since then, it doesn't look as extreme. So that's, that difference is the role of global warming in our discussion of long-term weather prediction. Let's see, whoops, I'm going backwards. Okay, this was just because I was going to mention El Nino. That's a forecast of the state of the Pacific, right? So we had our big, strong El Nino that peaked last fall, and it's been going away, and we're expecting a moderate opposite sign event, a relatively cool equatorial Pacific coming up next. So there's just an example of a long-term weather or short-term climate forecast. Okay. Moving right, yeah. And here's the associated temperature anomaly that goes along with that forecast. So we're expecting that this July will be pretty warm in Canada. And some of that is because of, so this is the El Nino signature for what you expect what you expect because of the condition of El Nino now for this summer. And that relates to the climate model prediction not that well. Right? So what this is saying is that our technology for predicting weather more than a month or so in advance is pretty much on the fringes of what we can possibly do. Okay, the last thing I wanted to talk about, with just a couple more minutes, is the impact of climate policy on the weather forecasting business. And this takes the form of two main issues. That at the moment, the main thing has been the impact of wind generation in the energy world. And so what you see on the right there is a chart showing energy demand in the Southwest power pool. And you can see that's up at, several, what are we approaching? Sorry, I can't even read my own graph because it's too small on this thing. It's probably tens of gigawatts of demand, something like that average. So this is the area and the chunk in the middle part of the country from Oklahoma through Nebraska and Kansas, that part of the world. And then at the lower line there is the wind generation over there. The Southwest Power Pool is a very windy part of the world. And the wind generation and there's a lot of installed wind power up there. So we're already at this point generating about maybe, what does that look like? About a third of the demand for electricity is being handled by wind generation over the Southwest Power Pool over the last few days and the next few days. Okay? So what that means is that if I am someone who wants to make a guess about how much money I'm going to be able to get if I sell electricity from my gas-fired power plant tomorrow, it's not enough to know that it's going to be a hot day. I have to know whether it's going to be a hot day and a windy day or a hot day and a still day. Because if it's a hot day and a still day, there's going to be much more demand for power from my gas-fired power plant. And if it's a hot, windy day, then there'll be much less demand. So you can't ignore that anymore. And the variability of wind is now as large an impact on the price of electricity varying from day to day as the variability of demand from temperature and so on. Solar is not there quite yet, but it's getting there. And it has this additional interesting factor that the sun is strongest in the middle of the day, and then it goes away at night, which means that there's this sharp increase and then fall off of solar generation from the middle of the day towards the end of the day that is faster than the demand falls off because people go home and go to bed and turn off their lights. So there's this period towards the end of the day when demand is still high but the sun has gone down, where it's going to be interesting to predict how the demand, the net demand, where you take demand and then subtract off solar and renewable energy, how that's going to play itself out. And then the final thing that's, so solar is not as big a chunk of generation as wind anywhere in the US yet, but it's ramping up at a very rapid rate, so that over California and the Southwest, people are very, very interested in the electrical industry about how they're going to manage to meet demand at every moment when this new variability signal has come into the electrical variation. The final thing that comes in on top of that is storage, which has not been a factor on the grid at all until recently, because storage is very expensive, so there's next to none of it. If we have too much electricity, we back off on generation. If we don't have enough, we make more. We don't put it somewhere and then get it back, with few exceptions. But as the electric car industry has pushed the demand for batteries, the possibility that peak consumers are now going to start buying storage for interesting reasons that have to do with electrical policy that maybe someone will ask about, means that people are going to have to think about how all those consumers will utilize that storage when they're thinking about demand. And that's going to have a really interesting and complicated relationship to weather. And that's the kind of cutting edge of how to think about the weather forecasting for energy demand problem in the coming years. And I think I'll wrap it up there. And thank you very much for your attention, and look forward to some good questions.
Okay, well, thanks to our panelists, and we have about 20 minutes for questions, and I think what I'll do, because this is being recorded, you ask a question and I'll repeat it, and then let the panelists answer. And I see a couple hands, the young lady over there. Mm-hmm. Okay, the question is basically, are there ways, more non-technical, down-to-earth ways of describing this difference between climate and weather in a way that could be easily conveyed to the average person? I'll let the relationship between everyday weather and climate change.
Yeah, I'll take a shot, and then Dan can take a shot as well. Climate and weather are different, but they're related. Climate is about the statistics of weather, how often certain types of weather occur. And this is where the Hanson analogy of the colored dice come into play. As the climate changes, it's going to change the probability of getting a certain type of weather. It's going to make cold winters less frequent and warm winters more frequent. But it doesn't necessarily mean that you'll never have another cold winter or there'll never be another heavy snowstorm. So just as we realize, to use my analogy from baseball, that even a weak hitter can occasionally hit a home run, as climate change alters the probabilities of certain kinds of events, we may still see big snowstorms, cold summers, cold winters, but they're going to become less frequent. So whenever somebody is talking about a single event, they're talking about weather. Climate is the statistics of those events over a longer period of time. Dan?
Yeah, the joke version of that is climate is what you expect, weather is what you get. Right? But, it is a really interesting question, and the way we talk about and frame these issues has a huge amount to do with the way we're trying to approach politics, right? Do we want to generate a sense of emergency around people and talk a lot around, terrible extreme events, floods, fire, so on and so forth? Or do we want to talk about this is a concern, the world is we are causing the world to warm up. If we waited 100 years and didn't do anything about it, the climate that our grandkids would inherit would be less pleasant for them in many ways? Or do we want some kind of a hybrid between those things? I think so in response to your specific question, what I say in those contexts is, leans towards the second answer. That, yeah, sure, last winter was cold, but, as Tony said, these are statistical things. We expect less of those winters over time. I would emphasize that there are some things that relate much more clearly to the forcing, right? The forcing is this long, steady increase in carbon dioxide over time. And similarly, we see a long, steady increase in sea level rise over time. And as in the example of Sandy, that has very real implications. It had implications for the New York subway system, which probably would not have flooded because there's a real threshold there, right? Did the water get high enough to get into the subway stations? And that happened partially because sea level had risen about a foot because of global warming. And similarly in Florida, where they're getting big problems to do with that. I'd love to talk more about that, but let's leave some room for other questions.
Okay, thank you. Let's go with the gentleman over there who had his hand up before. Okay, the question is the level of confidence of predicting different types of events. Is it really based on the amount of data available or some other factors?
So it's both. We call it global warming for a reason. The direct effect of putting carbon dioxide in the atmosphere is to heat the lower atmosphere and the surface. So when we talk about things like temperature, they are more directly linked to the cause than things like tropical storms or other types of extreme weather. But it's also related to our ability to observe things. We've had weather stations measuring the temperature in roughly the same way using very similar methods for over 100 years. But when we think about hurricanes, for instance, today we observe them with satellites, with radars, with planes that are flying into the center of those storms. Whereas before the 1950s, we didn't really have any of those things. So establishing whether or not a change is occurring is harder for some types of extreme events than it is for others.
I would just add that the other issue is that how would we answer the question, will doubling CO2 cause there to be more or fewer hurricanes and weaker or stronger? Right? The way we would answer that question would be make a physical model of a hurricane. Right? But our global climate models, which give us the most fully worked out answer to what is the consequence of adding CO2 to the atmosphere, until recently could not make a hurricane. They could make sea surface temperatures that were appropriate for hurricanes. They could make large-scale storms, like the kinds of storms that bring us a snowstorm in the winter. But they could not actually form a hurricane because they didn't have the resolution, the spatial detail to do that. I think our global models, now we're running global models for a century that will make hurricanes, right? So you have a climatology of hurricanes in the model, but they're still not at the level of our weather forecast models, and even those, for a global model, tend to be run at, say, 10-kilometer resolution, which maybe has a single grid point for an eye, right? Instead of actually resolving the motions within the eye or within the eye wall, more importantly, of a hurricane. So, I would be very confident that in 15 years we'll have much more confidence about what the impact of warming the planet by adding CO2 to the atmosphere is on hurricanes, because we will have models that can confidently generate a world with actual hurricanes whose statistics match the current observations.
Okay, let me go over on this side, the gentleman in the white shirt. Okay, the question is about a common climate denialist claim that water vapor is such a larger portion of the atmosphere that changing CO2 is not going to have any significant impact. I think this one is fairly easy to answer, but I'll let one of these gentlemen answer it.
So how many equations and PowerPoint slides can you put into your op-ed? No, water vapor is a greenhouse gas. It's a very potent greenhouse gas, and there is a lot of water vapor in the atmosphere. The difference between water vapor and carbon dioxide is that the amount of water vapor in the atmosphere can change with temperature. And what both models and observations show is that the amount of water vapor goes up when the temperature goes up. So when you add carbon dioxide to the atmosphere and you raise the temperature, that produces a feedback in which more water vapor enters the atmosphere, which is a greenhouse gas that further raises the temperature. So the difference is we can control the amount of carbon dioxide in the atmosphere. The amount of water vapor in the atmosphere responds to the temperature.
The only thing I'd add to that is just that the CO2 forcing, although, yeah, it's smaller, like if you just purely judge the number, like how much warming in the current atmosphere comes from CO2 and how much from water vapor, yeah, it's probably a bit more if it comes from water vapor. But the fact is, doubling CO2 isn't a trivial forcing. Even with zero feedbacks, it warms the Earth on average by about 1 degree Celsius, which is, you know, 1/5 of the way between our present climate and the Ice Age climate, right? So these numbers in a global context aren't small. And, you know, because of what Tony says, with feedbacks added, it has a bigger impact. It pushes the water vapor around.
I want to add just a little bit, because I've wrestled with this problem writing letters. One of the things about water that is different from CO2 is that water condenses at temperatures which exist on the Earth. And so it comes very quickly out of the atmosphere in the form of precipitation. So as these gentlemen said, it depends mainly on the temperature, whereas CO2 doesn't do that. If you add CO2, it stays there. Water vapor goes up and down with temperature. Okay. Okay, thank you. Let me find somebody in the back, the lady on the end there. Okay, on the left side. Okay. The question was, how good is the analogy to smoking and cancer between, in relation to the probability of weather events and global warming? Any comment from the gentleman?
It's not a bad, I think it's not a bad analogy for a particular event, right? Some terrible thing happens and you ask, you know, was that because global warming. But I think it's a little, I would be a little concerned about it in terms of talking about the big problem, because it implies that either we'll all die or, we'll escape. Like maybe nothing will happen, or maybe it'll be a big catastrophe. And I don't think that's not really the uncertainty, right? We know that carbon dioxide is going to make the planet warmer. We know that if we don't do anything about it and just continue to burn fossil fuels willy-nilly, the outcome will be in the net bad for a whole range of reasons. So that's the only caution I'd give about that.
Yeah, and there are other analogies that I've used, and different things work with different degrees of success, I guess. One that sometimes is colorful, at least, is you talk about somebody wearing a blindfold crossing a road. And if there aren't many cars driving up and down the road, there's probably a pretty good chance that they'll get across without anything happening. But there's also the chance that a car could be coming at just the wrong moment and they'll get hit. But clearly, if there are more cars on the road, the chances of getting hit go up. And that's, again, relates to the idea that climate is about the probability of certain weather events happening. You can get that record cold spell just like that blindfolded person could possibly make it across a busy road without getting hit.
We have time for one more question, so let me take, oh boy, I'm going to pick the gentleman in the front here.
So hard to read. Because it's a new science, or is it because I'm getting old?
The question is about event attribution, and why is it so hard to understand? Does it have to do with the difficulty of writing or age? Well,
I'll answer the part about the difficulty of writing, and Dan can answer the age question. No, I think, of course, scientific papers are being written for relatively small audiences. I think that's the reality of it, that they're being written for other experts. And this area of event attribution is a newly developing area of research. And it does involve statistics, and it does involve models. And so both of those contribute to it being very technical. So all joking aside, I don't think it's about your age. Now, Dan, maybe you disagree.
No, I agree. I think it's a fairly opaque literature, and part of that is just because it's a hard problem, and they're trying to make fine decisions about, they're just saying, well, what's the confidence level? We think there's something here, but we're not really sure. And also, it's contradictory, and that's frankly frustrating. I'm not a statistics expert. I really should know much more about it because of my youth and inexperience. I don't know as much as I ought to, but I think. I'm very hopeful that we're going to get clearer about this. There's a very nice effort, you probably know about this, but Climate Central is working on setting up an operational attribution project where essentially they're running weather models all the time with sort of alternative scenarios. What would it be like if we had climate change, and if we hadn't warmed up till now versus what it is like in fact, and asking, would this event have occurred, under a range of probability. So there are efforts underway to have a just continuous stream of answers coming in. Well, this event was like a red star event that really wouldn't have happened without climate change. This event, could have happened, And I think as things like that happen, as we get more practice with this, I'm hopeful that there'll be better efforts to make this clearer to a larger audience, and also just to get better at it.
okay, we've run out of time, and I want to thank everybody for coming. I'm sure there's a lot of other questions. Perhaps you could connect with our guests, but let's hear it for Dr. Tony Broccoli, Dr. Kirk Davidoff, and enjoy the rest of the conference.